Welcome to Chapter 2 and our Week 3. Today we are talking about fundamentals of data and signals. If you consider, in general today, the direction that technology goes to, there are huge needs for storage. I mean, consider even how we deal with music today, right? You might buy a CD-ROM with music, but then you rip it right away so that you can have it available on your mobile devices. And then you might upload the same music to Google Music. You might upload the same to Amazon. What's that? Or yeah, well, storing it on Amazon Music or Google Music would be a cloud, but there are other cloud services that allow you that storage. So what we see is that we tend to duplicate the same files over and over again, and these cloud storage companies, they have to come up with more and more space. Music is not even the big producer of storage. What do you think produces the most storage needs? Video, yeah, video. And look at YouTube. I mean, if there is a way or a system that change how we learn, YouTube is it. I remember trying to figure out how to windsurf, okay? I went on YouTube and I looked up how easy it was, and then found out that it's actually really, really hard. But you can learn a lot of things just by watching it, and it's so much different than reading a book, right? You could read a manual and get lost in it very soon, but you have someone show you. So video, really, video, pictures are also consuming a lot of storage. So the first thing that we want to talk about today is data, and data today typically is stored in digital format as zeros and ones. Why do you think that is? Why do you think that people tend to store data in a digital form? Okay, so a lot of our readers, a lot of our players are all digital. That's correct. Any other reason for storing data in digital form? Well, think about storage in analog format. What would be an example of storing data in analog? What's that? Okay, so let's say that you're recording tape and or maybe your vinyl music. Yeah, so those are all good examples of analog storage. Maybe picture on the wall, your Mona Lisa, that is analog storage, and it has some limitations. Right? You can't really take the Mona Lisa picture and compress it and put it away somewhere. Right? It sort of needs to be displayed as is. So digital storage has these great properties where we can compress it, quickly duplicate it, we can convert it to many different forms, and it's easy to transport. Okay, so that's one reason why many companies today, even here at the college, we have a lot of paperwork on students going way back in years. Because when students come back and they would like to go to other schools, they ask us for transcripts. Well, we need to go and look up your grades for that. So we used to keep analog records where we basically write down your grade on a piece of paper and put it away into a vault, right? To get that piece of paper out of the vault, you're hoping that there's no rodents or otherwise mold or other issues that would cause loss of data. But basically, it's really difficult to deal with analog storage. Once we can digitize these records, now that can be done by retyping them into a database or maybe scanning them. And there's great business right now to digitize records, right? So we take the analog records, we scan them into PDFs, we can provide descriptions, we can provide digital ID numbers so that when a student calls, we don't have to go to the vault, we just say, show me this record, and it shows you the PDF. Okay? So today we tend to store data with zeros and ones. But the zeros and ones, okay, are at the very bottom of the set of layers that will follow. Now last week you'll recall we talked about networking layers. Okay? Today, let's start with zeros and ones in terms of storage. Okay, so at the very bottom we have zeros and ones. In fact, Let me just open Notepad to do this with. All right, so we have some zeros and ones. Now these zeros and ones are going to be physically stored somewhere. See, and here's where we run into the first issue with the digital storage. When I store my data like I'm doing right now in Notepad, where is this data stored right now?
On your RAM right now.
Exactly, it's on RAM. If I turn off the power, whatever I typed in here is going to be gone. So right now it's in a temporary storage inside of memory. To store it on the more permanent media, what would I have to do? There you go. So now I would have to go through File, Save, and let's call this maybe in Documents, My Records. And now my data is actually protected better because I moved it from just my RAM, which is really temporary storage. I moved it into the hard drive. When I unplug the power, those zeros and ones will still be there because the zeros and ones become magnetic signatures on the hard drive. Either there is power or there isn't. But having said that, see, over periods of time, long periods of time, even the hard drives could lose the data. Or I could take a magnet and move it across the hard drive, in fact resetting the zeros and ones randomly, right? Which effectively would destroy my file. So what are other ways to store these types of zeros and ones in a more permanent, more resilient way? You could, so you could put it on a CD, on an optical disc, maybe not one, but multiple, right? And so you put one in your house and another one a mile away, so that way if there's an explosion or something, you're not losing all of them, okay? Any other way to do that?
Convert it back to analog and have it on tapes, like that's what they do in the movie industry and the salt mines.
Okay. All right, great. So we could now consider moving it to different formats. And perhaps if this is a picture, and well, it could be a picture, we can take an analog screenshot of that or a picture of it and keep it in a completely different format. Yeah. So one way to do this well is through a process of redundancy, right? I have a single copy on this hard drive. I will simply make multiple copies, one maybe on an optical disc, one on a flash drive, and then spread them out. If you think about it, in years past, many books were protected that way. You know, think about some scrolls that were written years and years ago. They would make copies of that scroll multiple times, so that multiple copies, as they're spread across maybe multiple countries, one of them is going to survive, right? Or at least later, you can compare them to see which ones were unchanged. Okay, so we do this today as methods of backup. You want to have a backup to tapes, but you might want to have another backup to disk. You might have a mirroring, which basically means that every time I write a file, the same file is written into another location, right? But at the bottom of our storage, there are zeros and ones. And oftentimes, these zeros and ones, all by themselves, are fairly safe. Because without a key to know what these zeros and ones mean, they might not be usable. In other words, if I encrypt my files, I still have zeros and ones on the disk, right? It's just their sequence is so convoluted that you won't know how to open it up. So the zeros and ones are stored on the disk, and that's the first layer. In networking then, when we move over data, we just move over the zeros and ones, and we rely on additional layers to pick up and understand what those zeros and ones are. So above the zeros and ones, we would find encoding, okay? And there's a whole set of encoders that help us. You might be familiar with ASCII, okay, which is a very simple encoding. You basically take the letters on our keyboard. These letters then are translated into numbers, and then those numbers into digital bits. Fairly simple. unless you're from another country where you have additional letters that are not on our keyboard, that are beyond that ASCII range, and you have to come up with a different encoding scheme. Okay? So encoding then would go on top of it. So there's some kind of an encoder, and now the encoder will take the zeros and ones, and it might turn them into characters. And these characters could be, Chinese characters, any type of next layer that we might need. Now, once the encoder is set, programmers, maybe the programmers who wrote Microsoft Word, are going to use this data to actually create meaningful information. So now, when I open the file, maybe it's an HTML page. Okay, the page is going to be written with ABCD and so forth, HTML tags. Okay, it's the program then, the application above, okay, the application layer that's going to deliver the meaningful information. So we are now looking at the process and the difference between data and information. Okay, data is basically something that's stored, something that can be copied, exists, but it only becomes information when we transform it in some way, when we massage it, and then it can be used by human beings to make a decision to actually have value. Okay, and that's information. Now later on in this class, we will have an assignment through a company called NetApp, through NetApp University, and as a result you will actually get a certificate of completion of one of their courses. We will look at storage fundamentals, okay, where you will be able to look at how today those zeros and ones are stored in a very, very efficient way. I'll give you an example. There's a technology that NetApp uses called Snapshots. Okay? Instead of having a hard drive in the server, today in a data center, people would use local area storage networks. Okay? It's a refrigerator size computer with hard drives in it, and these hard drives then are served to multiple servers as storage, and it's done all through the network. So a particular server might be using maybe a terabyte of disk space, and that disk space is not on the server, because if the server burns down, we just duplicate it. We still have that storage on the SAN, on the storage area network. But the question here is this: if I have 1 terabyte of database data files, how long is it going to take me to copy it, to duplicate it? How long do you think it takes to copy a terabyte of data? Like if I want to just do a backup, It'll depend, many variables, yeah, but it's not going to be in seconds. It might not be hours, it might be days. I'll give you an example. I'm doing a project right now with a school in Chicago, and they have 4 terabytes of storage that we are moving to another system in Virginia, to a hosted system. And it takes us 50 days to copy that. Okay? Multiple reasons. It's not just the network speed. It has to do with the way the data is stored currently in a ZFS file system on Solaris, which is not performing very well. Okay, so it's taking us 50 days to make that copy. So this is a common problem among storage systems, that there are so many zeros and ones that to make a copy it takes forever. So here is what people at IBM who now own NetApp are using. They're using a snapshot, which means that instead of making the entire copy, so imagine that this is our 4 terabytes and this is sitting on the server. Instead of waiting for every 0 and 1 to be copied before we say, okay, now we have a copy of it, they'll basically put a marker to say, okay, this is version 0, and from now on, we'll allow 2 copies of this data to be forked. So now we are going to do a snapshot, and the first person who is using the first snapshot, they might have this data now. Okay, And so this is going to be our customer A. But customer B, who is using the same data, okay, they choose to have just one extra one. Instead of duplicating anything, they basically are just going to track from now on all the changes that customer A and B are creating. See, so in a split second, they said, okay, we already duplicated everything for you. We had 4 terabytes of data, and now we have 2 copies of it. And as customer A is using it, we just track all the changes that they're making. As customer B is using the same storage, we're just tracking the changes that they're making. So to customer A and B, it actually looks like they have their own copies of the data, when in fact they're using the same data to start with, and we only create the changes for them. And that's called snapshotting. Very interesting way of doing it. Another way of making sure that data in these large systems is working well is to do deduplication. Okay? The way that works is, since we have multiple files, we look for patterns in the file, and if 2 files look exactly the same, and if they're exactly the same, we are just going to store one of these files. And the other one will be just a pointer to say, okay, if someone is asking for this file, that file, exactly. But it saves in terms of how many of these zeros and ones we actually saved. It's called deduplication. So later on, when we talk about these NetApp technologies, you'll be able to learn more about some of the solutions to the data problems that we have. All right. So let's switch gears, and at this point, let's talk for a moment about signals. Because data is like the thoughts that you have in your head, okay, just the thoughts. The signal helps you then to express and communicate the thought somewhere else. Today, when you have something to say, you might say it aloud and create a physical wave through the air, right? As I speak, I basically move the air nearby my mouth, and that movement is replicated through waves, just like you throw a stone in the water. There's a wave that's created through a medium, and for us it's the air, and then you can hear it because the wave arrives at your ear, and there are moving parts in your ear, a membrane that's hit by those waves, air waves, and those moving parts in your ear then create a signal that will arrive at your brain and then encode it or decode it and translate for something meaningful. Well, that's what we want to discuss in terms of electromagnetic waves. Whereas the waves that are sound require the air, and you may know that sound does not travel in outer space, right, because the air is not there. Electromagnetic waves do travel through space. Okay? Electromagnetic waves can travel through the air, but we can also send signal through a cable, okay, because there is a medium created there, and we can produce a wave inside of a cable. There are 2 types of signals that we want to discuss. One is analog, and one is digital. Okay, analog signal is going to be a perfect type of signal. Basically, it allows you unlimited shades, unlimited changes. Okay, that's very important because today, when we watch digital television, we're sort of settling on certain quality. In real life, the shades of colors, the shapes, and so forth are outlined with perfect lines. There's unlimited amount of changes that are possible. So here's an example. Let's see. Somewhere here we'll find an example of a wave. And this right here would be an analog wave, because notice an unlimited amount of settings that we have as the wave continues. Okay? The more focus, the more zoom on this wave, okay, we'll be able to notice more and more points that are present. These types of waves are great. In fact, if you consider music, when the music comes from the actual instruments, your violin, your cello, our ear can detect that really sounds great. It's an analog sound through an analog medium, because now the air becomes the medium, and our brain says this is really great. Or when you look with your eyes, okay, there's no replacement, because that's an analog reception. But there is a problem with analog lines and signal when it comes to transmission, okay? Because when we transmit information, we tend to run into things like noise, which basically are external elements that change the wave. Simply, if I speak and someone else is speaking at the same time, you will not be able to hear it as well at the end of the class. That's just an example of noise. There are other examples of noise. There's also something called attenuation. Okay, and this is present with digital signal and analog. As I speak, the further away from me you are, you can hear me less and less. That happens over a wire as well. If you just have very, very long wire, there's attenuation, which means that at the end of the long wire, the signal is going to be so weak that you may not be able to determine when the wave is up and when the wave is down. Okay. So let me ask you this question: Why do you think we went from the analog television to digital television? Because if analog is so great, okay, then why in the world will we go to digital television? Yes. What's that? Because it's 8 bits at a time? Okay. Okay, so it's faster than analog. Okay. Any other reasons why that change? Yes.
It's less susceptible to errors.
Excellent. Less susceptible to errors. Yes. And I've asked this question in the past, and I got different answers like government. Scheming and so forth. Although there's a lot to be said that the analog waves require a lot of different sets of frequencies. So with digital television, they were able to free up frequencies for other use. So someone's going to make some money, selling those licenses. But here's the big difference. If you consider an analog wave as we have right here, okay, this analog wave, sooner or later, as it travels through the air, let's see, there's going to be a picture somewhere here. As the wave travels through the air, it's going to encounter noise. All right, I'm sure there's a good picture here somewhere that I'm going to... Okay, so this is the wave that we start with, and you can see a television, basically, in order to put together the colors and the sound, it needs to be able to detect the ups and downs and the values of the wave. But once the television set is far away from the transmitter, and maybe it's in the valley where there are physical obstacles, the noise which is introduced might change that wave, so now it looks like this. Now the television will have no way of determining which part is the noise and which part is the actual correct signal. Therefore, the data that it extracts from this wave is going to be inaccurate. If you live close to the transmitter, it'll be great. But if you live, which is mostly the case, we live further away. Today's cities are built in such a way that there's always some big building in front of you. Okay, so this was experience of most television viewers. Basically, you could not get a good picture, and there's a whole lot of reasons why it's very important that basic communication like radio and television are of good quality. So digital signal provides us with a big advantage. In the digital signal, we only send zeros and ones. We don't have to worry about anything in between. So now the zeros are a flat line at the bottom and the ones are a flat line at the top. When we introduce noise, the same noise as before, okay? When we introduce noise to the signal, the noise is still present, but can we figure out which ones are zeros and ones? The answer is yes. So we can have error detection and error correction inside of our television that is going to flatten these lines for us. And therefore you can have clear picture even though there's a lot of noise present between you and the transmitter. Okay? So that is the power of digital signal, and that's why digitization of different forms, whether it's picture or sound, makes sense, because when we transmit this in digital form, we can actually ensure that it arrives on the other end and it can be decoded, it can be, the errors can be corrected easily. Here is an example of the level of noise where you basically cannot fix the errors anymore, right? So digital doesn't fix it completely. There will still be remote homes and locations where the digital signal basically doesn't come in. The other advantage of the digital signal is that we can now apply all kinds of tricks to the wave. For example, the zeros and ones, they can transmit not just a single channel, but these zeros and ones can have a section of it that belongs to this channel and another section that belongs to another channel. Just like on the train, you have multiple cars. One company puts something in this cart, another company in the other cart. When the train arrives at the destination, we can sort out what belongs where. Okay, and so that is an advantage of digital signal. We can also compress digital signal, right? Just like we might be able to zip a file, we can zip the file on one end and unzip it on the other end. And the better the compression mechanisms, actually it means we can put more data through the digital signal. Excellent. So what we are looking at here are the basic properties of a wave. And again, the wave is going to be there whether this is a digital signal or analog signal. Okay? The wave can be either spread out or it can be bunched up, and that's called frequency. Okay? Frequency basically means how many revolutions of the wave are there per second. So the faster the wave is moving, the higher the frequency. Let me give you this example. If you consider an instrument like the piano, okay, and the long strings on one end and the short strings on the other end. The long strings represent lower sounds, and the short strings represent high sounds. Okay, the longer strings, as they rotate, okay, they are going to have a lower frequency. Right, that's lower frequency. It's higher frequency for the small strings. But you can see that the long string, okay, and its frequency basically is related to how many revolutions are going to take place. So we use frequencies with wireless transmission. If you go to your little wireless access point at home, you'll see that you can use multiple frequencies to set it on. Perhaps the person next to you is using the same frequency as you do, and then the waves are interfering with one another, see? So you then change the frequency. The other property of a wave would be its amplitude. Now this time we're not changing the length of the string, we're just changing how hard we're hitting it. When you hit the string really hard, it's going to change shape in a greater way. The sound is louder at that point, but the frequency doesn't change. The length of the string doesn't change. So that's what we talk about in terms of amplitude. You can see these waves being taller, but they're bunched up the same way. They're not spread out. When they're spread out, then we change frequency. When they're getting taller, we're changing the amplitude. Which basically takes us to our car radio and the FM and AM labels. Does anybody know what these are stand for? What's AM and FM, please?
Amplitude modulation and frequency modulation.
Exactly. So amplitude modulation or frequency modulation Amplitude being how strong, how much voltage is on the wave, or frequency of how many revolutions per second. And the idea with the amplitude modulation and frequency modulation is that, first of all, these are not digital signals, they're analog signals. And we might find an example here. There it is. Okay. So we have a signal that's analog, and we have a carrier wave. Here is the wave, and perhaps this is frequency that you tune in on the radio, maybe 96.1, okay? And as we tune into this frequency on the radio, we can't have the frequency change on us. So what we can do is the same frequency can change its amplitude, therefore creating another wave on top of it, which is the actual music and the talking, whatever the data is that the radio station is passing to us. Right? So we tune into the frequency, but the amplitude is changing. And that would be our amplitude modulation. Okay? We can do the other changes where we change the frequency modulation, where we tune into another carrier wave, and then the frequency changes within a specified margin, and that's how the carrier wave then is able to bring the music and the talking. So those are the tricks with analog signal. As we go forward, though, let's see. Let's talk about how the analog signal becomes digital. One way to create digital representation of analog is to take samples of it, or snapshots, and then just include the snapshots as a set of zeros and ones. Here's an example of a perfect wave. So here is music that comes maybe from the piano, okay? And we have now a machine that can determine, okay, what is the amplitude, what is the frequency of that key that's being struck on the piano, and in a specific period of time, we basically take that measurement. A moment later, we take another measurement. A moment later, we take another measurement, another measurement. So we basically are slicing this piece of music and taking measurements. This is called sampling. And you might be familiar with sampling rates. But what we see on this graph is that if sampling takes place too far apart, then in fact, we are storing really not enough data about this music piece to get a good representation of it later on. With this sampling rate, notice that we are missing this entire peak, right? If we were to try to then undo this, okay, we can't just draw straight lines between the points. So let's say we start here, I draw a straight line, 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 right? So once we go through this process of pulse code modulation, we are able to create digital sound. The way back is really is going to include a lot of art, okay? Because we have to have a program now, software, that can figure out, you know, how much of a dip needs to be put in here, and where perhaps did we miss the peaks. And so then a program called the Kodak is going to take the dots that we saved, and then it'll try to reproduce the artistic value between the dots. So we can see that the higher the sampling rate, the less of that thinking we have to do. At the same time, companies that are in digital picture and digital sound, maybe like Sony, they are going to create software that is going to, better or worse, basically resolve these unknown areas between sampling rates. All right? All right, let's take a few minutes now. Go ahead and log into Blackboard, and there's an assignment there called sampling rates. You can use the textbook or you can use anything on the internet to answer the questions, but basically you'll have certain devices and then you have to provide the sampling rates for them. Okay, so based on the sampling rate lab, what we should notice is that when you have higher sampling rates, you get more accurate picture, more accurate sound, right? At the same time, notice that even at the lower sampling rates, our ears get confused just fine. You know, it sounds to us like fine music. Or when we look at digital picture, oftentimes it just looks fine. You know, 32 frames per second, and we're good with that. So that's why digitization in art, in entertainment, works so great, because it's easy to fool our senses so that our brain basically fills in the spots, you know, the missing information. In addition to sample rates, here's another way of modulating an analog wave. You see, this time we are not taking measurements in specific periods of time, but we are saying, okay, is this wave going up or is it going down? And that's the only thing we care about. We store a 0 when it goes down, or we store a 1 when it goes up. So notice that we can do that, and so our zeros and ones are going to be square. So that's the limitation of zeros and ones. And so we go up when the wave goes up, and then we go down and we go up. When the wave goes down too fast, this particular method fails because our modulated wave is unable to go down that fast. But this is just another way of trying to create digital signal, right? Another way of creating digital signal. All right, we also need to talk for a moment about the encoding. So once we have the zeros and ones, right, encoding then helps us to reach the next layer. And ASCII is something that will come back throughout this course too. Basically, every character in A, B, or C is going to relate to a specific set of zeros and ones. That's what ASCII is. But it's limited. It worked fine in the 70s and 80s when primarily the English language was the subject of computing. But today, we're going to use something called the Unicode. Actually, it doesn't show that many examples, but the Unicode has more examples in the textbook on page 55. Here is a good example of Unicode. Notice some of the characters that only exist on the Macintosh, or not characters, keys, right? So these keys right here have a Unicode number. So when you write a web page, you can use this number, and then the browser is going to show this new character that's not on the keyboard. Now, if you have a Macintosh computer, then under this URL, this will actually show an apple. It doesn't do that on Windows because the Unicode number is there, but Windows doesn't know how to display it. Right? So if we were to download maybe text that's in Chinese, if our browser doesn't know how to translate that Unicode number into a picture, then it does us no good. And A, B, and C, and D are all pictures. See, that's where fonts come from. Someone can take a brush and create a new A and a new B. They're all pictures. So that's how we go from zeros and ones to something that we as humans understand and can then decode. So you have to use some encoding scheme. And obviously this Unicode is more powerful. It's going to cover more ground, especially as we see global commerce, where you need to be able to have applications that reach people that have a need for new pictures in order to communicate with them. All right, let me just scroll down here. Excellent.